Assalamualaikum. Today we'll be presenting our CHM256 project on volumetric analysis, the determination of ascorbic acid in orange juice. Our team consists of 4 members, Putri, Tihani, Nadira and myself, Tia. The main objective of this experiment is to determine the precise concentration of ascorbic acid or vitamin C in an orange juice sample, and we achieve this by using volumetric analysis via redox titration with a standard iodine solution. In this method, ascorbic acid is our analyte, the substance under analysis, while the standardized iodine solution is our titrant. We are looking for the equivalence point, which is the exact moment when the added titrant is chemically equivalent to the amount of vitamin C present. Next, the practical application here is the quantification of vitamin C in commercial fruit juices. This comes with a challenge. Vitamin C is highly unstable and degrades rapidly when exposed to heat, light, and atmospheric oxygen during manufacturing. Finally, let's look at the industry significance of this analysis, which focuses on 3 major areas. First, quality control. This involves auditing factory batches to ensure legal compliance and processing retention, making sure the product meets regulatory standards. Second, nutritional transparency. This means verifying that the product packaging accurately matches the actual real-time vitamin content inside the container so consumers aren't misled. And third, public health. This is crucial for safeguarding consumers' access to active, vital nutrients in their daily dietary items.
Now I will explain the technical theory behind the ascorbic acid titration, which is based on a redox reaction. Ascorbic acid, also known as vitamin C, acts as a reducing agent, while iodine acts as an oxidizing agent. The chemical equation shown here represent the reaction between ascorbic acid and iodine. During the reaction, ascorbic acid is oxidized into dihydroascorbic acid by losing 2 electrons and 2 protons. At the same time, iodine is reduced by gaining 2 electrons and forming iodide ions. Because the amount of iodine rating is directly proportional to the amount of vitamin C present, this redox reaction can be used to quantitatively determine the concentration of ascorbic acid in the sample. The image shown here illustrates the color change observed during the titration process. Let's talk about reaction stoichiometry and quantification. The beauty of this reaction lies in its stoichiometry. The balance equation shows a perfect 1-to-1 molar ratio. This means that for every single molecule of iodine that reacts, exactly 1 molecule of vitamin C is destroyed. Once we know the exact concentration of our iodine and the volume we pour from the burette, we can directly calculate the exact moles of vitamin C in our orange juice. Next, I will explain the indicator selection and endpoint mechanism. Fruit juice samples are naturally yellow or orange in color, which can make it difficult to observe the endpoint directly. Therefore, starch is used as an indicator because it is highly sensitive to iodine. During the titration, any iodine add reacts immediately with ascorbic acid. As a result, no free iodine remains in the solution, and no color change is observed. Once all the ascorbic acid has been completely consumed, the next drop of excess iodine remains free in the solution and reacts with starch. This forms a permanent dark blue-black starch iodine complex, indicating that the endpoint has been reached. Therefore, the appearance of the blue-black color confirms the completion of the titration and allows the vitamin C content to be determined accurately.
Today, I will explain the experimental procedure for determining the concentration of ascorbic acid, commonly known as vitamin C, in a sample of orange juice. Key measures needed: orange juice sample, iodine solution, distilled water, starch solution, and standard lab equipment such as beaker, aluminium flask, and a burette. First, we measure exactly 5 ml of the orange juice sample using a pipette and transfer it into a clean aerosol flask. Next, we add 150 ml of distilled water to the flask. We do this dilution to thin out the intense orange color of the juice, which will make it much easier for us to see the final color change later on. First, we measure exactly 5 ml of the orange juice sample using a pipette and transfer it into a clean aerosol flask. Now, we add 4 to 5 ml of starch solution to our mixture. Starch acts as our chemical indicator. Right now, the solution does not change color because starch only reacts with free iodine, and there is no iodine in the flask yet. Now, we add 4 to 5 ml of starch solution to our mixture. Starch acts as our chemical indicator. Right now, the solution does not change color. Fill a 50 ml burette with a standard iodine solution. We record the initial volume reading on the burette before we begin. We begin the titration by slowly dripping the iodine solution from the burette into the flask while constantly stirring it. As the iodine enters, it immediately reacts with the ascorbic acid in the juice, turning into colorless iodine. Because it reacts instantly, the solution stays clear and does not change color yet. As we keep adding iodine, the ascorbic acid eventually gets completely used up. The moment the color change, which is turn blue, stay permanent, we stop the titration immediately. Record our final burette volume.
Now, I will present the results and calculation for determining the ascorbic acid content in orange juice using iodine titration. The iodine solution had a molarity of 0.005 molar. 5 milliliters of an orange juice was diluted to 150 milliliters, and 10 milliliters of the diluted sample was titrated with iodine using 4 milliliters of starch solution as the indicator. 3 titrations were performed, giving titer values of 18.90 milliliters, 18.70 milliliters, and 18.80 milliliters, with an average titer value of 80.80 milliliters. Since iodine and ascorbic acid react in 1:1 mole ratio, the ascorbic acid content can be calculated from the average titer. First, the number of moles of iodine was calculated using the formula number of moles equals molarity multiplied by volume divided by 1000. Using the average titer value of 18.80 milliliters, the number of moles in iodine was calculated to be 9.40 times 10 to the power of negative 5 moles. Because the reaction follows a 1:1 mole ratio, the number of moles of ascorbic acid is also 9.40 times 10 to the power of negative 5 moles. Next, the mass of ascorbic acid was calculated by multiplying the number of moles by the molar mass of ascorbic acid, which is 176.12 grams per mole. This gives a mass of 0.0166 grams. Finally, the percentage of ascorbic acid was calculated by dividing the mass of ascorbic acid by 10 milliliters of orange juice and multiplying the result by 100. Therefore, the orange juice sample contains 0.166% per volume of ascorbic acid. For discussion, the concentration of ascorbic acid obtained in this experiment was 0.166% weight per volume using iodine redox titration. This value was higher than the commonly reported vitamin C content in commercial orange juice. The difference may be due to the variation in the orange juice sample preparation, storage conditions, or the presence of other reducing substances that may react with iodine during titration. Experimental errors such as endpoint detection and burette reading errors may also affect the accuracy of the results. Overall, iodine redox titration is a suitable method for determining ascorbic acid concentration in orange juice. In conclusion, the concentration of ascorbic acid in the orange juice sample was successfully determined using iodine redox titration. The final concentration obtained was 0.166 weight per volume. Therefore, the objective of this experiment was achieved. That's all from our group. Thank you for watching.